Okay, so this is PowerPoint 2 that deals with acid base. And now we're going to look at what this weak and strong acid base thing is. And hopefully it'll come through. I guess it can be a little I know it can be confusing. It's how you look at it, and from the view you got to take a look. But and some of it's almost counterintuitive. A lot of times you think one way, and it's the opposite. So so what determines what a strong acid is acid that breaks up into H plus and the negative ion completely, and it always will stay the plus, H plus and the minus. There's no reforming of the original acid. Okay, so that's in the case. So the reaction goes completely to the right. So that's why you only have the single arrow. Weak acids, on the other hand, they break apart. The H plus comes off, but what it does, it can reform with the base to form the original acid. Okay, so a weak acid doesn't completely dissociate or ionize, and so that's those two. Now, a base strength is related. So a strong base will grab a hold of an H plus really well and kind of seek it out and grab it. All right. And a weak base, not so much. Okay, it won't do all that much. So those are different classifications. So what we're gonna do is we're gonna look at a complete reaction. Acid. So the acid turns into conjugate base, and the base turns into conjugate acid. And we're gonna specifically just look at the acid turning into conjugate base, and why what is it about that makes an acid a strong acid? Okay, and it's going to actually relate a lot not to the acid itself but to the base. Okay, so I have a kind of cartoonish thing here where you have the shapes here. So you have the acid H with the diamond is added to this base, which is just a square, and undergoes the acid-base reaction, and the H plus comes off the acid, joins with the square, so now it's the conjugate acid, and the diamond has been left with the electron that the hydrogen has left when it's to join. So what I really want to focus on here is the conjugate base, because the acid to reform, the conjugate base has to almost want to grab hold of that H plus off of the acid. So the conjugate base, if it's going to be a strong acid, the original strong acid, then the conjugate base has to be weak. That means it's not going to be able to grab a hold of that H plus that well. So a weak acid, which a strong acid forms, okay, and they're related, okay. So a strong acid always produces a weak base, a weak conjugate base, and that's because the weak base doesn't turn back into the acid. It doesn't have the ability to do that. And so since it can't do that, the acid can't reform, So essentially, a weak conjugate base determines if an acid will be strong or weak. So if you have a weak conjugate base in a base that has an inability to grab a hold of H, and there's a reason for it, it's not a bad thing, is that then the acid can't reform, and the acid therefore is a strong acid. The way I've kind of realized is that a strong acid isn't really what's important here. Okay, it doesn't make the strong acid isn't what makes a strong acid. It's actually the conjugate base that makes the strong acid, because if this conjugate base can grab a hold of an H and become the acid again, then the acid isn't strong. But if the conjugate base doesn't grab a hold of H that well, then the acid will appear that it's strong. So the weaker the conjugate base, the less it can reform into the original acid. So the original acid doesn't reform and is a strong acid. Okay. And what we will look at, and this is one of the key things, and you know, if you, the more you get into acid base understanding, you know, if you take organic chemistry, you spend a lot of time talking about it, and you really got to understand it. It's about the conjugate base. It's not about the acid. Okay, it's about what it forms. If the conjugate base can't reform the acid for whatever reason, we're going to look at those reasons in a minute, and then you have strong acid. Okay. So whenever you have a here's a reaction. So acetic acid is a weak acid, and so what it does is it can release an H. Okay, and with water and form an acid base. Okay. So it's a weak. So what happens is that it forms a stronger acid. Okay. So that means, and you have to be told that. So you have the weaker acid turns a stronger acid. So the weaker acid will always turn into a stronger acid, and vice versa. So the weaker acid, when it turns into a stronger acid, the stronger acid is going to say, "Hey, I don't want this H. It's like a hot potato," and throws it back. And let me get my pointer here. So what it does is so you have your hydrogen here is a hot potato. It throws it over to this guy, and it takes it, and it goes, "Oh no, I don't want it," and it throws it back. Oh, okay. So whenever this guy gets the H, it throws it back because it's a stronger acid. It dissociates easier. So whenever you have a weak acid and a strong acid, the reaction will always lean towards going towards the weaker acid. And that's because the stronger acid says, "Whoa, I don't want this proton." All right. In general, stronger acids and bases tend to react with each other, and they produce the weaker conjugates. For instance, which we just talked about, I said a strong acid will produce a weaker base, and it's important. This is important here because the conjugate base, when it's formed, it doesn't grab a hold of H plus that well. So a strong acid will form a weak base because the weak base won't turn back into acid, keeping it towards the right. So don't think about weak and strong in terms of like strong and things like that. Just think about what's going on here is that the acid, in some ways it's almost, it's kind of backwards to me, is that the weaker conjugate base, weak means it sounds like it should just blow up, but actually it's very stable and doesn't need the H plus. And vice versa. Okay, so we're going to look into this. Why? What makes a weak conjugate base so good? All right. So what and that's going to be a key thing. Is so we always talk about these usually get talked about in terms of the base. I mean the acid, but like I said, the base, the stability of the base, the more stable the conjugate base is, the stronger the original acid is. That's because it can't reform, and it's going to be always going to the right. It just can't reform. All right, so let's look into that. So trends in acid strength. So there's kind of two things that determine the strength of acid, and there's electronegativity. And so we're going to look at a binary acid, HX, where X is one of these guys here. And one thing we notice is the acid strength increases as you go left to right in the periodic table. So what we're going to see is that as you go, this just kind of turn around, is that this is further to the left and this is further to the right. So this should be flipped, and maybe I'll do that after I'm done with this video. But chlorine has a higher electronegativity than selenium. It's further to the left. So this acid here, if it's HCl, has a higher electronegativity. HCl is greater, stronger acid than H2S, which is stronger than HP, and so forth. Okay, and why is that? All right. What makes this a strong acid? Okay, it's how easy it gives up an H. So in this case, we're actually going to talk about. All right, so when an acid gives up an H plus, this relates to electronegativity. When hydrochloric acid is put in water, the chloride, which has a strong electronegativity, will grab a hold of that electron from the hydrogen because it's a high electronegativity. And the electron is actually more stable on the chlorine than it was on the hydrogen because chlorine pulls it really close. So the H goes off without it as H plus. And the H plus may try to come in and grab a hold of that electron, but the chlorine wins because it has a stronger electronegativity. And so it keeps it in place. And so the chlorine can't, so the hydrogen, so the reason why this is a stronger acid is because the chlorine, again, the conjugate base, is able to stabilize the electron better than when it was on the hydrogen. So it's about the conjugate base, and in this case, the electron is more stable on the chlorine, and it says, "I don't want to go back with you, hydrogen. I'm fine." And remember, a weak base doesn't combine with H plus. All right. Okay, second thing that determines acid strength is the dispersion of the negative charge on the conjugate base. And we talked about this in 121 about charge density and dispersion. Okay, so let's go to it. So if you look at these three here, they're all HCl, HBr, HI. They're all in the same column. Okay. But HI is the strongest acid of these three, even though it has the lowest electronegativity. Okay, so HCl has a higher electronegativity now. Cl has a higher electronegativity, Br and I. And so what we just talked about, we said, the chlorine grabs a hold of the electron, and the hydrogen can't find it. I mean, can't grab a hold of it because it's a tug of war. Okay, in this case, the I grabs a hold of the electron, and because iodine is so big, what it kind of does is it just kind of flashes out that electron all over the place. So really we should be looking at this as Hi turning into H plus I minus. So I minus is a conjugate base, right? And that I minus is very stable for two reasons, but the biggest reason is that the atom is so big it can hide that electron. So if the H plus comes in and starts looking for that I minus, that electron on that I minus, it can't find it because it's spread out all over the place. Okay, so again, it's about the conjugate base. So the I minus is what makes HI a strong acid. It's not the HI essentially that makes the acid strong. It's what it forms. It's the conjugate base because it hides it. All right. So there's kind of two things here. So is that first of all, if the atom that's attached to the H can grab a whole electron and hang on to it really well, better than the H plus, then the H plus can't do it, and so it can't reform. And then and then if the negative ion can spread out the charge, then it also can make it hard for the H plus. So, the weird kind of thing about this is we say a strong acid forms a weak base. To me, actually, a weak base is very strong because what it does is it hangs on to the electrons and it doesn't let the H plus get with it. So that's where it's kind of confusing to me when I was learning this. Okay, so there are acids which are oxyacids, and these guys are the what I call the tertiary acids, and they have many oxygens on them, like phosphoric acid, sulfuric acid, and things like that. Well, these guys are very strong acids, and the reason why they're strong acids is because they form very weak bases. Okay, and so what we're going to do is look at the first case. Well, so these are oxyacids or oxoacids. So we have these three guys here, and what's common between them is they're all acids, the H, and they all have 4 oxygens. The difference is what is the other center atom attached to it. Okay, so the chlorine here has the highest electronegativity, and so what it's going to do is hang on to the electrons better. And what it does is just kind of spreads out the electrons. So in this case, the electronegativity of the central atom increases the acid strength or increases the weakness of the base. Okay, same thing here. Electronegativity. So these are all in the same row, and these are all in the same column. So the element with the highest electronegativity always will be the stronger acid and weakest base. Okay, can just look at them more, but now let's look at changing the number of oxygens. All right, So let's take a look at this guy here, this nitrogen OO. And really we should have is the conjugate base. So this as a conjugate base would be this knocked off and this knocked off over here. And how that negative charge can move around. And so so after the hydrogen is left, you're left with that negative charge. And in this case, what happens is the electron, because the oxygens are really electronegative, the electron is attracted to both oxygens, and it's kind of spread out between all three of these atoms. Okay, well, this guy has 3 oxygens plus nitrogen, so that one electron, it gets spread out all over the place, so its density becomes smaller. And it's kind of, again, it's harder to find the electron because all it sees is a spread out charge, not a single charge. Okay, when these guys form the conjugate base, which I really think is probably more important than anything here, a negative charge gets pulled towards the oxygen and stabilizes in the negative charge because of electronegativity. So that's the first thing is that the electrons get pulled away from anything out here, and they're like, I'm happy with all these things. Okay, and the more oxygen you get in, the electrons get all stuck in there, and so it's, if you have a H plus out here after you knock this off, okay, it's harder for that H plus to go and find that electron. So reducing the charge density is on the conjugate base is a big deal. All right. Okay, so in 121 we talked about resonance structures, and I spent a lot of time on them, and I told you guys they're really important because what they do is they stabilize add electrons and pi bonds. And what they essentially do is they hide these electrons in the pi and add electron, and it sort of puts them in the forest, and it's really hard to find them. So phosphate is formed from phosphoric acid. So H3PO4 will turn into phosphate. So you have these 3 H pluses are floating around here looking for negative charge. Well, I know there's 3 minus charge here, but when you look at it, those 3 minus charge are all sort of just all hidden inside here. And so the H pluses come by and go, I can't find it. All right, I can't find it. And so they don't attach and they don't reform. So this is a weak base because it doesn't reform with the H pluses that well. That means the acid, original acid, was strong. Okay, so this is kind of another way to think about it. Again, so again, what I should do is it should knock this guy off here. I really should pay attention to the conjugate base. So if you knock this away and just leave with the negative charge here and here, okay, what happens is that negative charge gets split up basically between these 3 hydrogens. So it has basically that one charge isn't just one charge anymore. It's like negative 1/3. And this guy, it's even more. It's only even less, negative 1/4. So the more oxygens you have, the more spread out charge that is. And it's harder to find, and it's harder to reform with the conjugate base. Okay, so let's just do a little exercise here. And so we're going to look at these 3 guys and see which one has the highest, the strongest acid. Again, what you really should think about is the conjugate base. And okay, so what we want to do is what these guys have in common. They're all acids. This H3 can be in front. And And another way they're related is that they're all in the same row. Okay, so if they're all in the same row, what determines the acid strength is the most stable conjugate base will be the one that has the highest electronegativity. So HBr is the furthest right. Okay, so that means it has the highest electronegativity. And so HBr is the strongest acid of all these because it forms this most stable conjugate base. All right, this group here, these are the oxy acids, and they all have the same amount of oxygen. And again, the difference is the center atom and its electronegativity. Okay, so what you're going to do is you're going to look at electronegativity to determine the strength of the acid. All right, so these are all the same columns. So sulfur is higher up and has a higher electronegativity than selenium and beryllium. Okay, and then finally, these four, okay, they all have HBr and O in them. What's different is the number of oxygens. Okay, the more oxygen, the more dispersed the charge on the conjugate base. Okay, so really, again, you shouldn't really pay attention to the acid. It's the conjugate base. So BrO4 minus is more stable than BrO2 minus, Br minus, or BO3 minus. And that's because it stabilizes that negative charge, spreads it out, and makes it harder for it to connect. Okay, next part is type of acid. It's called organic acids. In particular, these things are called carboxylic acids, and they have a formula that looks like this. There, right there. Okay, and they're often given as COOH, COO. And if you take organic chemistry, you would spend a lot of time talking about these guys. All right, so this is a acid. So when you put it in water, what happens is this H pops off, with the proton pops off, leaving a minus charge, then the extra electron here. And so what you want to do is what can stabilize the conjugate base. Okay. All right. So what you want to do is what you add here is going to help stabilize that negative charge here. Okay. So you can put, so there are different ways to do it. One way you can do it is you can put a high electronegative atom here. And what it'll do is it'll start pulling the electron towards it, so it's harder for the H plus come by and find it and grab a hold of it. And so if you take a look at these guys, these four here, they're all similar, is that they all have this CO2H, which is this right here. And what's different is they have the CLs attached. This has 3 CLs, this has 2, this has 1, and this has none to this out here. Okay, the more CLs out here, what it's going to do is it's going to pull the electrons out here after it's lost its H, and it's going to stabilize that electron. Okay, so the one with the most electronegative atom is going to be more stable than the other ones. So this guy's this is the strongest acid, or the weakest, or gives the weakest base. Again, the weakest conjugate base, which means the most stable conjugate base. Okay, this down here is the weakest acid. Okay, and that means the conjugate base can find the electron really well, strong, and reform. All right. Okay, and the final part of this tape, this PowerPoint is this problem here. So let's take a look at these 5 guys here. So this is a carboxylic acid. We call organic acid. COOH. COOH. And what's different is the N group. Okay. The N group has to be able to draw electrons towards the best. And there's 2 ways, okay? The way that we show here, and there's a dispersion way as well, but is that the higher electronegativity is going to pull the electron after it's lost the H. It's going to keep that negative charge here from being, it's going to pull it and drape it all over this thing. And so it's going to be harder for the H plus to find it individually. This guy up here, the electron is just, after it loses H, it's just hanging out here. The H plus can come here and grab a hold of it and reform the acid. Okay, so that's PowerPoint number 2. Hopefully it turned out good. And we'll go to number 3.